So what we'll be talking about today is just a brief revision on space physics. Then we are going to look at some questions that we are going to answer at the end of the lesson. So let's be prepared, and I want us to please be 100% attentive. Please, let's be 100% attentive so that we can be able to do the class task at the end of the lesson. So please confirm if you can see my screen.
I can
I
see.
can it.
Okay, that's a very good one. Thank you for that. Since you can see my screen, I think we can continue. So basically, right, it's not like it's a new topic or a new point of discussion. It's what we have introduced ourselves to. I'll just quickly brush it up. Then at the end, we are going to look at some questions. We'll attempt some question on space physics, IGCSE question that will be expected to see in the exam. So we have introduced ourselves to the Earth and the solar system. We have seen that the Earth is a planet that rotates on its axis, and we have also emphasized that the axis is tilted, and because it is tilted at about 23 degrees Celsius or so, then we use it to explain the observation of the daily motion of the sun, then periodic cycle of day and night. And we have also learned too that the Earth orbits the sun once in approximately 365 days, and this bring about periodic nature of seasons. Now, please, I want to um, advise us that we should make sure that um, our syllabus is handy. We should always go through the syllabus because the syllabus help us a lot in understanding some concepts we need to cover for the exam we are preparing for. So please make sure you always have your syllabus whenever you are studying. Even while you are going through the past question, it's also okay for you to go through the syllabus. It's also fine, and that's why I'm just using it to revise with us briefly. So please make sure you have your jotter with you because I'll ask us to take note of some things as we continue. So the next point is for us to know that it takes approximately 1 month for the moon to orbit the earth, and we can also explain the periodic nature of the moon's cycles and phases. We are not going to dwell on that now. Then the next thing I would like us to take note of is the definition of average orbital speed, and we have the equation before us. So if you have your jotter with you, please write down the equation for the average orbital speed. Please put down the equation quickly. Average orbital speed. Put down the equation. Welcome, Manar.
Thank you, Mr. Nyono.
Yeah. So we've
Good
not gone
afternoon.
far. We've not gone far. We just started. So that's the
Okay.
first. That's the first screen we are sharing already. So we have
Okay.
looked at. We are just revising space physics so that we'll be able to look at some questions at the end of the discussion. It won't take long. So now the what I want us to jot down now is the average orbital speed, and the average orbital speed is given by this equation: V equals to 2 pi r over t. The r is the average radius, and that average radius of the orbit is also known as the distance of the earth from the sun. You can refer to, if we are using the orbit of the earth and the sun now, so the average radius is going to be the distance of the earth center from the sun. So that's the average radius. So that means if we are given the distance of the earth from the sun, that will serve as the average radius. Then the second variable there is t, capital T, like uppercase T, and that is the orbital period. And the orbital period is the number of times, if we use Earth for example, the number of times the Earth is able to the time taken for the Earth to rotate through the sun, to complete one rotation, time taken to complete one rotation, that is the t. So please take down this formula. It is always coming out. It is always coming out both in the theory and in the objective question. So please note down this equation. And the question I'm going to give you at the end of this lesson, you are also going to see this particular equation where we need to apply it. So it's very important for us to take note of some of these points that I am talking about. So the next point of call we need to look at is the solar system itself. If you have a question, you can let me know. The solar system itself, we have mentioned before that the solar system contains one star, which is the sun. The solar system we are talking about is our own solar system. Where is this coming from? Okay, that's fine. Okay, we refer to our own planet and the planetary body as the solar system. Our sun and the planetary body is referred to as the solar system. We have many other form of other solar system in the universe or even in the galaxy. Now we are looking at our own solar system now. In our own solar system, we have one star, which is the sun. We also have 8 named planets. We are meant to know it from the order from the sun, and these are things we have been playing with since our key stage 3. Then we also have the minor planet that orbit the sun, and this minor planet could include the dwarf planets like the Pluto, and could also include the asteroid in the asteroid belt. Then we also have moons that orbit the planet themselves. Then we also have other solar system bodies like the comet and the natural satellites. Then we're also meant to learn about the we should compare the different part of the solar system. The first four solar system, we are meant to compare it with the last four solar system. And what is the comparison? Like for example, the first four solar system, they are rocky, like they are made up of rock, and they are kind of small in size. And the further four planets that are far away from the sun. So that is to say, the first four planets, they are rocky and small. Then the fifth planet to the eighth planet that are further from the sun, they are gaseous and large. They are gaseous and large, and this can be explained through the accretion model for solar system formation. An accretion model for solar system formation emphasize that the model emphasize that the solar system is formed as a result of gravity pulling different elements of dust and particles. So from different elements of dust and particles, then as these dust and particles continue to rotate in cloud, it forms what we call the accretion disk. And it's the accretion disk that continues to form that at the end of the day bring about the formulation of our current solar system. I think we debated a lot of this in class. I remember very well. So it's just a form of reminder again. Then we are meant to know that the strength of gravitational speed depends on two factors. One, it depends on mass of the planet. That is to say, if we have a big planet, a planet that is very big is going to have a very, very high gravitational field strength. Then we also know that the gravitational field depends also on the distance from the planet. That is to say, if an object moves away from a particular planet, the gravitational field strength will also reduce. If an object move away from a planet, the gravitational field strength of that planet on that object will be reduced. That is why whenever a rocket is leaving the earth, as soon as it gets to a point far from the earth, it enters the space. The gravitational field strength of the earth will not be able to pull it anymore. So two things that affect gravitational field strength: the mass of the planet and the distance from the planet. They were also meant to learn how to calculate time it takes light to travel a significant distance between solar system. We are going to look at that subsequently. That's light years. We'll look at that in a moment now. So just take note of that too. We are going to see it clearly now. They were meant to also know that the sun contains most of the mass of the solar system. So they can ask us in an objective question that which of the planetary bodies contains most of the mass of the solar system? Very straightforward, the sun. And that is why it is the sun that is able to pull all other planets as a result of the gravitational strength of the sun on all other planets. We said that the bigger the planetary body, the higher the gravitational field strength. So the sun being the largest in terms of mass of all the planetary body, because of its high mass, it is the one that have the high gravitational field strength to pull all other planetary objects towards it. Then we should also know that the force that keeps objects in orbit around the sun is gravitational attraction of the sun. That's just an emphasis of what I just mentioned now. Then we're also meant to get the fact that planets, minor planets and comets, they all have elliptical orbit. I think this is also another objective question that will always come our way. What do you mean by elliptical orbit? It simply means that the orbit is not a perfect circle, it's not completely round, it is bent at some point, it is oblique at some point. So we should take note of that concept too, very important. Then they will give us data to analyze, like planetary data. They will give us to analyze in terms of orbital distance, orbital duration, like how it is rotating, then the density, how heavy it is, the surface temperature, the uniform gravitational field strength. One of the questions we are going to do at the end of this lesson, we are going to interpret planetary data. So I want to encourage us to try as much as possible to be expectant to see something on the planetary data which we are going to interpret. Then the next point of call is the stars and the universe. Of course, it's not a debate anymore. The sun is a star. And it will interest you to know that within the universe, the sun is just a medium-sized star. It's not like it's the biggest star or very big star. It's just a normal medium-sized star. And the most common element in the sun is the hydrogen. In fact, the hydrogen is the fuel. Thank God we have talked about fission and fusion. And we are able to emphasize that fusion, when two elements come together to form a bigger one. So the hydrogen is the fuel that fuses together to form helium. And the result of that fusion nuclear reaction gives the high amount of energy which we're using in the surface of the earth right now. And we have also, they said that the sun radiates most of its energy in the infrared, visible, and ultraviolet regions of the electromagnetic spectrum. So I'm so excited that these terms are not new terms to us. They are terms that we are already used to. So let's just be following up. Then we're also meant to know that stars are powered by nuclear reaction that release energy, and that in stable stars, the nuclear reaction involves the fusion of hydrogen into helium. So this is also an emphasis of some of the things that I've been mentioning and I've been talking about. So we move forward. So just for me to know that we are all together with me, I want to call somebody to read the next one for us about the star. So who is available quickly to read for us? Stars. State that. Who is doing that for us quickly?
Me
Thank you.
states that galaxies are each made up of many billions of stars. The Sun is a star in the galaxy known as the Milky Way. Other stars that make up the Milky Way are much further away from the Earth than the Sun is from the Earth. Astrono- Astronomical distances can be measured in light years, where one light year is the distance traveled in the vacuum of space by light in 1 year.
Okay, thank you very much. So please take down this point. Please jot this point quickly. Jot this point quickly. Astronomical distance, like distance in space. That's what it's trying to say. Astronomical distance is trying to tell us that distance in space can be measured in light years. Astronomical distance or distance in space is measured in light years. So 1 light year is the distance traveled in space by light in 1 year. So if light is able to travel in 1 year, the distance traveled in 1 year is given as the light years, and the value is given to us there. Number two, that's the value. Know that 1 light year is equals to dash. Who is reading out the value for us? What's the value of 1 light year? Quickly, it's given there in the screen. Can you read it out for us? Who is good? Anissa, do that quickly.
1 light year is equals to 9.5 times 10 raised to the power of 13 or 15.
15.
Yes, 15 meters.
Very good. So please take down that too. Put it down as a point that 1 light year is equals to 9.5 times 10 raised to the power 15 meter. That is huge. 10 raised to the power 15 is like um that's trillions kind of. So that is huge. So 1 light year, the distance traveled in space, 1 light year is 9.5 times 10 power 50. Okay, Anissa, you have a question?
Mr. Femi, you mentioned something on helium and something concerning the
I
planetary bodies and helium. I don't understand what you're saying.
Okay, very good. What I mentioned about helium and hydrogen specifically, I mentioned about helium and hydrogen. I said that the solar system, our own solar system, or generally speaking, every star is powered by hydrogen fuel. Are you getting the point now? So, and I said that it is as a result of the fusion reaction. That's, remember, I've talked about two types of nuclear reaction: fusion, coming together of element, and fission, breaking of element. So we said that the stars have been powered, like the stars are shining as a result of the reaction between hydrogen and hydrogen, formation of hydrogen. I mean, hydrogen and hydrogen fusing together to form helium. So currently, as the sun is shining on us now, is because hydrogen and hydrogen fuse together to form a new element called helium, and that gives a large amount of energy, and that is why we can get light energy and heat energy from the sun. Anissa, is that okay now?
Yes, sir. Thank you.
You're welcome. Okay, now the next point of call for us to look at is we want to describe the life cycle of a star. So please, if you can screenshot this, please take note of this. Very important. This question is like a compulsory question in most of the questions that I've seen, most of the past questions I've seen. If you have gone through all of past questions, you realize that this question is a compulsory question. Life cycle of a star, we must be able to describe it. So the first point is a star is formed from clouds of gas and dust, and mainly hydrogen. That's the first point. You may like to jot it down. Then, when these clouds, we can also use the concept of accretion model, like the clouds and dust, they keep moving around in a circle as a result of gravitational force, which we are going to look at later. Now, after that, a protostar is an interstellar cloud collapsing and increasing in temperature as a result of its internal gravitational attraction. That is to say, as hydrogen, dust, and gas particles, they are moving around in a circle, the internal gravitational attraction continues. And as the internal gravitational attraction continues, the internal energy will also increase. And that brings about increase in temperature too. So when this process continues, the protostar is now able to become a stable star. And that stable star can be achieved when the gravitational attraction, which I just talked about, is now balanced by an outward force due to high temperature in the center of the star. Remember, as the particles are moving together, as the particles are moving, are rotating due to its internal gravitational attraction, there is an increase in temperature. So when the gravitational attraction is now balanced by the external force, which is the increase in temperature, and this happens at the center of a star, that is when a protostar now becomes a stable star. So you can see the first process, dust and particles bring about the formation. Dust and particles are available for formation. Then a protostar is now formed when the dust and particles continue to move in their, because of gravitational attraction. Then when the gravitational attraction is now balanced by an external force or outward force that is as a result of the increasing in temperature as the gravitational attraction continues to speed up, then what we have is a stable star. Remember, in a stable star, the hydrogen is available to fuel the nuclear reaction, which forms helium. Now, after all the hydrogen available are now used up, the hydrogen available are used up, then the star will run out of hydrogen. And when the star runs out of hydrogen, what happens is most of the stars will expand to form what we call red giant. Please take note of all these points. If I were you, I would just have a an arrow to be indicating how these points are going. So when the star run out of hydrogen gas, it's formed what we call red giant. It will just be expanding. and form red giants. And red giants are more massive stars. They are more massive. In fact, they can even go to super giants. In this situation, most of the hydrogen in the center of the star has been converted to helium. So when most of the hydrogen have been converted to helium, the red giant from a less massive star will form a planetary nebula with a white dwarf star at the center. That is to say, it's going to be forming another dust and particle again. That's the planetary nebula coming to pass again. So remember, star is like a cycle. It's not like the formation ends at a point. The formation does not end at a point. It's a cycle. It continues. When the stars are eventually formed, hydrogen is used up, it remains only helium, then it becomes red giant and super giant. Then what happens again is that another planetary nebula is formed. So the red supergiant explode as a supernova, and that will give us another nebula which has hydrogen and other heavy elements. So the result will now be what we call a neutron star or a black hole as its center. A neutron star or a black hole at its center. So the nebula from the supernova may now form a new star. So when the new star is formed again, the same process from what we just started from will continue start again. So that is how it continues on and on and on. For now, that is the basic assumption of life cycle of a star. Remember, science community is growing, and as the science communities grow, the more discovery they make, the more we adjust any assumption that seems to be inappropriate or not correct. So for now, this is how we have it, and researches are still going on. And as this result of research comes out, we'll get to know more about what is happening around us. So quickly, let's move on to the universe. So let's move up to the universe. Who is going to help us read universe number 1, 2, 3, 4? Who is reading for us quickly? Who has not spoken? Okay, thank you, Manaro. Thank you.
Know that the Milky Way is one of many billions of galaxies making up the universe, and that the diameter of the Milky Way is approximately 100,000 light years.
Okay.
Describe redshift as an increase in the observed wavelength of electromagnetic radiation emitted from receding stars and galaxies. Know that the light emitted from distant galaxies appears redshifted in comparison with light emitted on the Earth. Know that redshift in the light from distant galaxies is evidence that the universe is expanding and supports the Big Bang theory.
Okay, thank you very much. So, from what she has read for us, the first thing I would like us to take note of is the concept of red shift. Now, what do we mean by red shift? So, the red shift comes as a result of the idea of the fact that the universe is expanding. Please take down that point. So, the red shift um, is an evidence of the expansion of the universe. And how do we describe it? Remember, from the our electromagnetic spectrum, the visible part of the electromagnetic spectrum is composed of Roig beef. That's the seven rainbow colors: red, orange, yellow, green, blue, indigo, and violet. Right. So now the red shift is telling us that the observed wavelength of electromagnetic radiation that is emitted from stars that are moving away from us. Some stars are moving away from us. So they now observe that the wavelength from those radiation of those stars is now increasing, moving from the lower part of the spectrum to the red part of the spectrum. Remember, the red part has the highest wavelength, and down to the what, to the lower part, which is the what, violet. So they now observe that the wavelength of those electromagnetic radiation from those stars is moving towards the red part of the Roig beef of the rainbow. So that is why they call it red shift. So is the wavelength is shifting towards the red part. It was initially towards the violet part. Now, as time goes by, when they observed how the wavelength is moving, they discovered that it's shifting toward that red part. And that's why they say we should describe redshift as an increase in the observed wavelength. So that means the wavelength is increasing, and as it's increasing, is moving towards the red part of the visible part of the electromagnetic radiation. And any star, so those stars from distance, as they observe their spectrum, the wavelength is increasing, and that shows that the universe is expanding. They also want us to know that the light emitted from distant galaxies appears redshifted. That's what I just finished explaining, in comparison with the light emitted on the Earth. Then the last part she read was that redshift in the light from distant galaxies is the evidence that the universe is expanding, and this supports the Big Bang theory. So they can ask you, what are the two things that support the Big Bang theory? The first one is the redshift. The next one is going to be the next one we are going to talk about. Let me bring it up quickly. We're almost there now. Then we go to our questions and answer. So the second evidence is that microwave radiation of a specific frequency is observed at all points in space around us and is known as cosmic microwave background radiation. Remember, we talked about background radiation during nuclear physics. We talked about background radiation. Now, another evidence of the Big Bang theory or universe expansion is the fact that at all points in the space, there are background radiation. And that is why whenever we are measuring radiation, we must always consider background radiation. At all points in space, there are background radiation. This is another question they used to ask. They can ask you to state two evidences of the Big Bang theory or the universe expansion. The first one is what? Who is telling us quickly? Just speak.
The red shift.
Very good. And the second one is the one we are talking about now, which is what? Microwave radiation, or you can call it cosmic microwave background radiation. Or you can just simply put background radiation, but it's fine to say cosmic microwave background radiation. Okay, Anissa,
Mr. Femi, you said they could ask us which question?
what are the two evidences of the Big Bang theory or expansion of the universe? Have you gotten it?
Okay, thank you. Yes, sir, thank you.
Excellent. Welcome, Aisha Idris. So basically,
She's not.
okay, let's continue, please. So basically now we have mentioned those things. Then another good point that we need to take note of is the speed at which a galaxy is moving away from the Earth can be found from the change in wavelength of the galaxy's starlight due to redshift. We are still emphasizing the same thing again. So that's also another emphasis of what we just talked about now. Speed at which galaxy is moving away from the Earth. You can calculate that speed by knowing the change in wavelength of a galaxy's starlight. Change in the wavelength. We just finished explaining that too. Then we should also know the distance of a far galaxy D, and it can be determined by the brightness of a supernova in the galaxy. So please, if you can note down this point too. So please note this point too. I think I've seen it in several objective questions too. That the distance of a far galaxy can be determined using the brightness of the supernova in that galaxy. And the last point of call, which we are going to look at, is Hubble's constant. Please write down this equation. All the years I have seen this Hubble constant coming out. All the years I have seen this Hubble's constant coming out. So please write down the equation of the Hubble's constant. So Hubble's constant is the ratio of speed at which a galaxy is moving away from the Earth to its distance to the Earth. So H naught, that's the Hubble constant, equals to V over D. H naught, which is the Hubble constant, equals to V over D. So take note of that point. Then Hubble constant, like they call it, is a constant, so we can know the value. So the value is very straightforward. So who is here to speak? Juaria, I need to hear your voice. Anissa, please, you ask your question now. Let me hear Juaria voice. Juaria, what's the value or what's the current estimate of Hubble's constant?
Um, H zero equals to V over D.
Good. So what's the current estimate? That's number 10. Read it out.
Oh, H zero is 2.2 times 10 raised to power minus 8 per second.
Minus 18 actually, please.
18, sorry.
Very good. So please note that value. They can ask you to state the value. They can ask you to tell us the units. Very important. And if I can ask your question now.
Mr. Fanny, the V over D is the speed over distance, right?
Exactly. Speed over
Okay.
distance. Exactly.
Okay. This thing, the thing you're presenting right now, I think you sent it on our Google Classroom. That's the scheme or the something, right?
Exactly.
You
Exactly. Is
sent
there.
it
Is there.
from months back.
Is there.
Mr. Femi,
Yeah.
this is the syllabus, right?
Exactly. It's the syllabus.
Okay.
Yeah. All right. So let's finish up. Then another thing is this equation. They rearrange Obus constants. Look at how they rearrange it. They turn just like they turn the Obus constant to an inverse, then they now inverted V over D to D over V. And this formula represents approximate age of the universe. So in like 3 past questions now, they have asked learners to calculate the approximate age of the universe. So if they ask you to calculate the approximate age of the universe, you can say age of the universe equals to distance over V, or 1 over Hubble constant. Either way can work. We are going to see some question to back that up now. So please put down this formula. We have seen the formula for Hubble's constant. Then we have seen the value or estimate of the Hubble's constant. And now we have seen another formula for calculating age of the universe. So you can rewrite it this way. You can rewrite it this way, please.
Mr. Fanny,
Yes.
you said they can ask us to find the age of the universe at per 2 years old age, AGE.
You said?
They can ask us to find the age of the universe, like age, AGE.
Yes. AGE. Yes.
So it's either the V over D or what?
Yes. V
One
over
over
D, or 1 over Hubble's constant.
oh okay.
So
This
in a moment, let me get something. Um, let me see if my pen. I don't know why my pen switched off. Let me put up my pen quickly. Let me see if my pen will work.
Mr. Femi, this current estimate for the Hubble constant, this 2.2 times 10 raised to the power of minus 18.
Exactly,
They
per
said is the
second.
current estimate per
Yes,
second.
yes.
So the V over D, the value always is the 2.2 times 10 raised to the power of minus 18.
Let me get you well again.
The current estimate is 2.2 times 10 raised to the power of minus 18.
Yes,
Does that mean the value of the Hubble constant is always equal to that? So whichever value they give us to find the Hubble constant, that will always be our answer.
exactly. That's what I'm saying. So
Oh,
remember,
okay.
they said current estimate. I know what that means, right?
Yeah, yes,
Very good. So
approximately, right?
exactly, approximate. So a new discovery may come. So you may change the formula to this way: T universe equals to, can you see what I'm doing? T universe equals to D over V equals to 1 over H naught. Can you see that?
Wait, Mr. Femi,
Yeah.
does it have units?
What? Time of universe?
No, the approximate age of the universe.
Yes, the unit is in seconds, or if I ask you to also give the unit in, I'm sorry, in years, so we can just do the conversion roundabout. You just also do the conversion. So this is time, and time is measured in seconds. So they can also ask us to leave it
Okay.
in years too, or maybe in
Okay.
days, depending on what they want us to do. Is that okay?
Yes, thank you.
Very good. So now we can move to the question that is before us. How many of you were able to? Okay, I posted the question on the Google Classroom, anyways. But since we'll be solving this now, so I'm going to post more on the Google Classroom. So let me see. Let me open another one for us quickly. Let me open the question for us to see. Year 11. Okay, very good. Can we see a different screen now? Or we are still seeing the previous? Okay,
Yes.
we can see.
No, that's yes.
Is it clear
Mr.
enough
Femi,
or I should expand it? Is it clear enough or I should expand it?
Expand it, please. It's okay.
Okay, fine. All right, quickly, let's go through it together quickly. So now this is a planetary information. So I'm just going to give us a clue and we are going to attempt the question. So let's be attentive. I'll give us a clue and we'll attempt the question. So now, table 9.1 gives information about 3 planets in the solar system. Now we are given the planet. We have the Earth, we have Jupiter, and we have planet X. Then they gave us the mass. The first mass, the mass of the planet Earth is 5.9 times 10 raised to the power 24 kg. Mass of Jupiter is 1898 times 10 raised to the power 24 kg. The mass of planet X is 4.87 times 10 raised to the power 24 kg. Then they gave us the average distance from the sun. Then they gave us orbital period in days, and they gave us the gravitational field strength. So let's brainstorm now based on this data. They want us to guess the name of the planet. They want us to guess the name of the planet. So let me give us a clue. Then somebody will help us to guess the name of the planet based on the clue I'm going to give to us. Now, the first clue is this. Let's look at first the distance from the sun. The distance from the sun. Which of the planets has the shortest distance from the sun? Who is helping us with that?
Planet X.
Look at it very well. Shortest distance from the sun. Look at all the values.
Distance.
Yeah, distance from the sun. Shortest. Look at all the
Planet X.
Is
planet
X.
X. X. Okay, very good. Planet X. That's correct. Now, since planet X has the shortest distance from the sun, it simply tells us that planet X has to be before the Earth. Remember? So, and look at the gravitational field strength too. It is 8.9, and gravitational field strength of the Earth is 9.8. Okay, anyway, that's for this next question. So with this now, somebody should guess planet X for us. Somebody should guess planet X for us.
Venus.
Venus. Do we all
Mm.
agree with that?
People should answer. Oh.
Let's answer now. Do we all agree with Venus?
It's correct.
Okay,
Yes, it should be
I agree with
correct.
Venus too. Venus is correct. So we have read the data to explain that. Now the next thing is they want us to describe the relationship shown in table 9.1 between the mass of a planet and the gravitational field strength at its surface. They want us to look at the relationship. Who can, not Manaro again, who next is going to speak now? Let me see. Um, okay, Isla, you are ready?
Eh?
Okay, so Isla, they want us to describe the relationship between the mass of a planet and the gravitational field strength at its surface.
Okay. So the strength of the gravitational field strength depends on the mass
In what
of
way?
the
What's the
planet.
relationship between them?
Like I don't know.
No, now is it that when the mass reduces, the field gravitational field strength increases, or what?
Yes.
You've not said anything, no. So what is the yes there?
I'm not sure.
Okay, who else is helping us? Look at the value. The mass of the Earth is 5.97 and the gravitational field strength is 9.8. The mass of Jupiter is 1898 and gravitational field strength is 23.1. The mass of X, which we have identified as Venus, is 4.8 and the gravitational field strength is 8.9. So now they are now asking us, what is the relationship between the mass and the gravitational field strength? Is it that as mass increases, okay, Manaro, thank you.
I think if the mass of the planet is high, the higher the mass of the planet, the higher the gravitational field strength at the surface.
Isla, did you get that now?
Yes.
So that is it. So you just, next time if you want to answer questions like this, look at the data given to you. You look at the data very well. One increase, the other increase. As the one increase, the other increase, then you can be able to reach a conclusion. So if they ask you to state relationship, always remember it has to be either direct relationship or inverse relationship. So don't just say, don't be vague that the mass depend on the gravitational field strength. In what way? So you have to explicitly explain in what way did the mass depend on the gravitational field strength. So please take note of that point. Very, very important. So let's look at the next question. They said we should explain why distance from the sun in table 9.1 is an average value. Look at it. They said average distance from the sun. Average distance from the sun. That's what they said here. So they are now asking us, why is it called average distance from the sun? Why can't they just tell us that it is distance from the sun? And I remember I mentioned it while I'm using it when I was saying something about the syllabus, that the average distance is, they use average distance. Let me just, because of our time, let me just give us a hint on that. Now it is average distance because the sun, the orbit, the orbit with which the planet move around the sun is not a perfect circle, is elliptical. So they cannot get the what, the exact value, because it is what, elliptical. That's why they give it average value. Please, is that okay now? Does that make sense? Does that make sense, please? Just give me an emoji, or you just,
Yes.
yeah, okay,
We
thank you very much.
understand.
Yeah. So now the next question is this. Show that the average orbital speed, show that the average orbital speed of the Earth is approximately 30 kilometers per second. So what's the first formula? Who can just tell me the first formula I'm going to write? Just tell me so that I'm going to write the formula. What's the first formula I will write for this question? Because they have mentioned a keyword there, average orbital speed. So
V equals 2 pi r over t.
excellent, thank you. So just have V equals to 2 pi r over t. So that's you've gotten 1 mark like that. How many marks did they allocate to it? Okay, I didn't note it. Most likely 3 marks. So now, what is our T? What is our R? Now, they gave us the answer. So they want us to impute the value to get this answer, which is 30 kilometers per second. So now you come here and look for your R. Your R is the average distance from the sun. So for the Earth now, the R is going to be equals to 149.6 times 10 raised power 6 kilometer. Remember, it is kilometer now. So what we are going to have now is this. Yeah, okay. So that will be equals to 2 times pi, can know the value of pi, times 149.6 times 10 raised power, what's that again? 10 raised power 6 kilometer. So since it's in kilometer, we can decide to leave, and the value they gave to us is also in kilometer seconds. So we can also leave it this way, kilometer over. So now the next thing is the period t. So they gave the value to orbital period in days. You can see they gave us the value in days. So we are going to convert it to seconds, because the unit of what they gave to us is in seconds. So that is in days, that is um 365.2. So who can remind us, how do you convert days to seconds quickly? How do you convert days to seconds? We are always brainstorming for us. How do you convert days to seconds? Why is Absat leaving my meeting now? How do you convert days to seconds? Who is reminding us? Days to hour to minutes, then to seconds. So what are the value are we going to use? What are the value we are going to use? Days, hour, minutes, seconds. Days, hour, minutes, seconds. Okay, we don't have too much time. Let me just help us out. Or someone is helping me out. So days to hours, 24, to minutes, 60, to seconds, 60. So this is what we're going to use. So if you input these values, you should be able to get your final answer. Once you input these values, you'll be able to get your final answer. So you may write this down and solve it later. You may write this down and solve it later, please. You can write this down and solve it later. So let's make progress to the next question. Let's make progress to the next question. Star,
Hmm?
Star, since you have unmuted your mic, you read the next question for us.
Complete the sentences about the life cycle of stars. Protostars are formed from.
What do you suggest would be the answer?
They are formed due to the movement of the particles of dust.
So dust and particles. Very good. That's correct.
Yeah.
You can call it nebula. That's very correct. Huh? You can call it nebula. So the B part.
Okay.
Can you remember how we explained the exam? A protostar becomes a stable star when dash is balanced by dash. Can you remember?
No.
Okay, try and remember.
So does it have to do with hydrogen?
In okay, it has to do with, remember I talked about, as they are pulling, as the gravitational force is pulling, then the gravitational force will now be balanced by the external um, force, external temperature. Can you remember I mentioned something like that?
Yes.
Good. So that is exactly how you are going to approach that question. So a protostar becomes a stable star when the inward gravitational force is balanced by the outward heat energy. Yes, that's more appropriate. Inward gravitational force is balanced by the outward heat energy. You can say that a protostar is formed. So let me see if I can quickly get that information um, from our page again. Okay. Okay, yes, formation of stable star. So look at it. A star becomes stable when the inward gravitational force is balanced by the outward force due to high temperature of the center of the star. So that's just it. If you have, if you have, you can take down that notes now. So a protostar becomes a stable star when the inward gravitational attraction is balanced by the outward force due to high temperature. So that is how it is. So the next question: the initial fuel used to power nuclear fission in star is what? Quick answer. What's the fuel they use?
Helium, hydrogen.
Hydrogen, please. It's not helium. Hydrogen is the right answer.
Hydrogen.
Okay, that's correct. They said that stars that are approximately the same size as the sun become red giant stars when then form a dash and a white dwarf star at the center. Just proton star. So that's just it. So you can see that question on formation, or what do you call it? Question, okay, neutron star. Question on formation of what? Sorry, life cycle of
Sir,
star are very
please, what
good.
did you say?
I
The
said
last question.
stars that are approximately the same size as the sun becomes red giant stars when they form a neutron star with a dwarf
Okay.
white dwarf star at the center. Neutron star. Neutron star. This is it. Neutron star. So what's the next question now? They said the Milky Way is one of many billion of galaxies. Each galaxy contains many billions of stars. Stable stars transfer energy into space by emitting electromagnetic radiation from their surfaces. Describe what happens in the core of a stable star to release energy that is eventually transferred into space. Simple. Nuclear reaction is happening. Hydrogen fused together to form helium, and it releases large amount of energy. Is that taken?
Yes.
Very
No,
simple.
sir, please say it again.
Okay. Nuclear reaction happens, that is hydrogen fused together to form an helium particle, which releases large amount of energy, which releases large amount of energy. So I'm going to leave us here to look at some other questions. I've seen question on Hubble's constant. The question is available on our Google Classroom. Let's go through it. In the next class, if you have any question, drop it in the Google Classroom. I can review this in the next class. Then in the next class, we'll pick something else. Or if you have more question on space physics, you can also bring it up. So generally, do you have any question before we continue? Any general question for the class? Any general question before we continue?
Sir, please, can you repeat the life cycle of a star?
Okay, no problem.
Exactly.
So this is it again. Describe the life cycle of a star. This is it again. So the first and the foremost is, okay, maybe I can just give us a summary. We can put down the summary. Star is formed for clouds of dust and gas. So this is it. One, dust, dust and gas, specifically hydrogen gas. Then from dust and gas, there is interstellar cloud collapsing and increasing in temperature as a result of its internal gravitational attraction. So collapse of the cloud of dust and particles. So you can put it, that's number two, collapsing of the nebula. This you can dust and gas are also called nebula. So instead of telling story, you can just use one word. Collapsing of the nebula. So this dust and gas can also be referred to as nebula. So let me put it this way: collapsing of nebula. Then the next point of call is protostar become stable star. So that means this collapsing of nebula is the protostar. Protostar. So the collapsing of the nebula is the protostar. So when the nebula collapse together due to the internal gravitational attraction, a protostar is formed. Then from protostar, you have a stable star. Stable star. So dust and gas, that's nebula, protostar, stable star. And stable star is formed, we have mentioned it, inward force balancing outward force due to high temperature. So after that, after stable star, then when the star run out of hydrogen, it's going to form red giant. Red giant or super giant. Red giant or red super giant. So when red giant or red super giant is formed, then the red giant will now form a less massive star. So that is, this happens when all the hydrogen has been used off, or when most of the hydrogen have been used off. So when most of the hydrogen has been used off, the red giant form a less massive star. Huh? So the less massive star plus white dwarf, white dwarf star. So less massive star plus white dwarf star. And after this, there will be supernova. That's explosion. The supernova explosion is the same thing as the Big Bang, actually. So there will be supernova. That's another explosion. Which leads to supernova, which leads to formation of neutron star. Neutron star or black hole. Supernova leading to formation of neutron star or black hole. Then the cycle continues again. Then the cycle continues again. That's what happened. So it starts another cycle again. So then another cycle starts again, and it continues like that, and it continues like that. And now, does it make a little sense again?
Yes, it does.
Very good. So I have the recording is going to be available for those who are interested. So they can I'll upload it where we can access the recording. So if you're interested, you can share. I'll share it in the classroom for those who are interested. They can go through it. I think with this we have covered reasonable ground on space physics. On Thursday, I'll look for another topic that is key that I feel we have not yet covered very well. So when we resume, it's just be revision galore, revision galore. We'll keep solving problem. We'll keep doing year 10 and year 10 work so that we can revise very well. I wish us all the best. So how was the class?
It was good. It was nice.
All right. Take care of yourself. Bye.